So, hello everybody. Welcome to a new live stream of this webinar format on binary cartography. Today, agentic malware analysis from task automation to deep analysis. The idea today is that after we took a closer look the last time on, let me check if the sound works. Yeah, good. So after we took a closer look last time at agentic analysis and agentic reverse engineering, today we take a look on how we can use agentic agents on specific for malware analysis. A few words about me. So I'm an independent security researcher, consultant, and trainer. I have a PhD in reverse engineering, and I mostly focus on code obfuscation, deobfuscation, and automation. And I mainly also give trainings on reverse engineering and software deobfuscation. So today we talk about what agentic malware analysis is. Then we take a look at various use cases like string decryption, API resolving, and multi-stage analysis. And finally, we discuss how we can go from individual tasks to large-scale automated analysis pipelines. So just a small recap. An agent is basically an LLM with a tool, with access to tools in a loop. So we basically have something like Cloud Code or Codex, and these are then we use these in Docker environments, such that they have control over the entire environment without creating too much damage. And then in this Docker environment, we have analysis tools. So like Ghidra or Binary Ninja and so on. And then they can autonomously operate in that setup, and we can chat with them and give them tasks. Last time we did that with the webinar on agentic reverse engineering. And there we had a fully fledged setup with a Docker container that basically spawns then a shell into the same directory and gives access to samples and all other things. So, and today we will have a quite similar setup. Today we will have like also a Docker setup with the run Docker script and a Docker file. And this Docker file will contain a lot of tools like Radar2, bin utils, core utils, and so on. But also either the Ghidra MCP server for headless analysis or the Binary Ninja MCP server for headless analysis. And I will be using today Binary Ninja and the Binary Ninja MCP. Mostly because it's faster and better suitable in a live stream. However, if you install that and you don't have a Binary Ninja setup available, it will automatically fall back to Ghidra. So today I brought a few samples with various difficulties that I would like to demonstrate how agents can support the analysis on these kind of samples. So, and let's start with some pretty easy one, Mirai. Mirai is basically an embedded botnet. And embedded botnet, that basically means it compiled this for the ARCH64 or ARM32-bit architecture. In this case for the ARM32-bit architecture, and it brute forces default credentials of usernames and passwords. So for instance, we can here we are in our environment. We can here just run the Docker container. Then we are now in the Docker container with the Binary Ninja API installed in the Binary Ninja MCP server. And then we can, for instance, spawn Codex, the client, the agent from OpenAI. And here on the same, we open it in Binary Ninja. And if we scroll in Binary Ninja and take a look at the strings, we will see that a lot of strings are quite look quite weird. So let's pick one of them. For instance, let's take for instance this one, and then we follow the cross-references. And if you follow the cross-references, we will notice that there is one function which is called several times with various things that look like encrypted strings. And if we take a look at that inside, we will then see that here we have a loop where we do a byte-wise iteration and a constant with the XOR of 0x22. So this is a typical string decryption routine. And what we could do now is we could do it manually, decrypt the strings or decrypt the entire string part and so on. But this is also a good task that we can easily give to an agent. For instance, what we could do is we could just take that address and go to an agent and tell it, analyze the malware sample Mirai in samples, use the MCP server. There's a string decryption routine. There's a string decryption routine in function and give it the function address. Decrypt all the strings and annotate the Binary Ninja database for further analysis. So now we could give it a task like that. So we basically took a look on our own. We noticed, oh yeah, there's a string decryption routine and that needs some work. And now we could go to agent, give it the task and press enter. And then now it will basically figure out the environment, find the binary, then here it already found it, then it will spawn Binary Ninja headless anytime soon, and then here now it spawns the Binary Ninja headless API, opens that, goes to the function, figures out what's going on, and so on. So this will take a while. I don't think it will take too long, but in some minutes we should have a good results, which we could of course have done on our own. Which we could have done also on our own, but the lesson here is that agents can help and support us in reverse engineering and save us significantly time. Let me look, there's a question. There's a question, will we cover what to do with the malware file if found for threat intelligence? How exactly do you mean the question? Maybe could you rephrase it such that I can answer more specifically? So in the meantime, we see that here it already figured out it's the constant XOR 22. So it now basically understood how it goes and starts with writing a script to decrypt the parts. So it's making already progress. While this is working, let us go to another example. So 2 weeks or 3 weeks ago, there has been a great blog post from Cisco Talos about an EDR killer called Killing. And this one is a pretty interesting sample. It has multiple stages. And in one of the stages, in the first stage, it also has some API hashing. So the idea of API hashing basically is that we want to hide imports that we like from third-party libraries or from Windows APIs. So what we do instead is we somehow load the module, and then we have some hard-coded code, which basically is that we walk over all exports of the module, and then we do something like a hash of the current export name. And if this is equal to a hard-coded constant, then we know that we have a match, and then we can import it basically and use it. So that's the idea behind import hashing. So, and we basically have to figure out a hash function, then the constant, and then we would come up with which module is imported, what are current exports of this module, and compute them in the hash until we find matching constants. And then we know basically the mapping. This would be the manual work. And if we take a look at queuing itself, here we see here there's a DLL base where we basically fetch some pointers to the DLL base. Then below here we do some nested function calls, and somewhere we call a hash function. And this hash function is then the underlying hash function that computes for the given string a value. And there's of course some code around about, and we see that there are multiple calls to that and so on. And now, once we figured that out, our idea would be to ask an agent to analyze the entire API hashing and give it, and then basically brute force it. So what we can do is we can go to an agent. Here we'll spawn on the right hand side, we'll spawn another shell. Then we can, for instance, say we trigger codecs again. And once we triggered codecs, we can tell analyze the queuing EDR killer sample. There's API hashing around the hash function at address Z. Analyze how it works, and then brute force all API hashes. So we can just give it a query like that, and now it will do the same process. We can just use the MCP server for that, and now it will figure out what's going on, load it, analyze the corresponding parts, and this will take probably some minutes. So we will just leave it as it is here, because if we do that manually, it might take us some minutes or some hours. So now we gave it a task, and after a few minutes, we will probably have useful results. Let me answer some questions on the side. So why do we need to run agents inside a Docker? Well, technically we do not need to run agents inside a Docker. However, given that an agent has full system access, it can first read all the files in the file system and probably send it to a cloud provider. And maybe they are secrets or private documents or things that you didn't want to share. This is one thing, like the privacy aspect. The other aspect is if you run an agent without control on your production system, it might delete files, it might break some functionality or so on, so it's kind of dangerous. And therefore, I would in general always recommend letting agents run into a Dockerized or virtualized environment that at least is encapsulated and sandboxed. And especially in the case of malware analysis, it's even more important. Otherwise, you might infect your own or something like that. Okay. This one here, it already identified now some of the imports and analyzed it. Let us go back to the other agent, which just has worked on the Mirai sample. And here it basically told us it's done. It analyzed it, it decrypted the strings and saved the annotated database, and it also renamed some functions and so on. So that sounds good. Now we can open it. We'll find it basically here. And if we open it, we indeed find two functions. And if we take a look at that, this is the decryption part. And here, if we now go to that one, we see that they added comments for the username and the password. So basically, this PMMV should be with XOR 22 root. We can just shortly validate that in Python. So let's open a small Python shell and let's do something like C for C in PMMV. And now we want to take the ASCII value of that character, XOR it with 0x22, and then again get the corresponding character. And indeed it's ROOT, so reading root, so that looks good. So we now basically verified that this one looks good. And as we can see, while we could entirely do that on our own, and there are multiple ways to do that, we could just tell an agent what to do, and the agent does some really nice work here. Okay. There's another question if I will let the agent dynamically analyze the malware sample. Not today, not in this stream, not in this setup, but maybe in a future stream. Okay, so let's go back to the other sample. Oh no, and this one is that agent. Let's go to that agent. This one is still working. So while this one is still working, let us now go to the third sample. The third sample is a multi-staged FinFisher sample. FinFisher has been a governmental malware, and there has been a great article from MSD International about that exact sample that we are taking a look at. And it's basically a fully fledged Trojan with some obfuscation, with multiple stages and so on. And it drops also a lot of files. So as we can see, there's a complex infection chain and so on and so on. And the sample we are looking at, this one, if we take a look at the main, this one will basically do some environmental checks somewhere in the subfunctions, drop a lot of different files if we would execute it dynamically. And finally, it starts loading and executing a shared object file called at.so. So, and we don't wanna infect us here. So, but we know that this one drops some files. So if we take a look at the strings, we will, for instance, see that there are a few .dat files that might be dropped. So, and we don't want to analyze the entire code, how exactly that works, and we want to run it. So what we could do is we could ask the agent. I'll take now the same agent as that did the Mirai thing. I just tell it new to start a new context. And then I tell it analyze the FinFisher sample. It's a multi-staged malware and it will drop various files. Analyze the extraction logic and statically extract all the files. Given that we are in a Linux environment and that the FinFisher malware is a Linux sample, we will just additionally tell it do not execute the sample or anything else, work purely static. And then we tell it also you can use the MCP server for analysis. And now it will again start working, analyze or open the sample first, then analyze it, and maybe extract it automatically. Maybe we have to intervene. We will take a look, but now this will work for a while. Okay, while that is working, let's go back to the other agent. And here we will see that it figured out already, like in 5 minutes of work. It figured out how the hash function works. It tells me where the module resolver is and so on. And it brute forced some of these things. So it did quite a lot of work. It also found the blog post, but it seemed to brute force the things on their own. So we could now ask it something like, are there any other API hashing that hasn't been resolved yet? And then maybe it will file something more, maybe not, but at least it resolved parts of that. And we can take a look at the folder. Maybe they also created some scripts that have been dumped in the file system. But here, no, we don't see any scripts having dumped in the file system, so that's good for now. Let's take a look. Okay, that sounds good. So now we can tell it, for instance, thanks, annotate the BNDB for further analysis. And now it will do similar as in the case before, where in the Mirai sample, it will now create an annotated database that we can work with. While that goes on, let's go back to the other agent and see what it does. It's still working, but it also identified what's going on, and it's creating a folder. So let's inspect that folder. It's not there yet. It put it into another folder. It is sampled, so it's in the root. There it is. So there we have the FinFisher folder. And under dropped, we found that it dropped a lot of files. And we can take a look at the files. And we see that most of them are just random data. And there's one ELF file there. Okay, so it dropped then. So it basically now extracted all the files. So, and we have another stage that we can analyze. So let's open that new stage. So we go to dropped and analyze that one. And here we will see, first we notice that there's some anti-debug code here. We see that we don't have too many functions, only a handful or two handful. So we can skip a bit and we will see that here's a slightly obfuscated function. Here we have a larger function that looks obfuscated. Here too. And then we also find, like if we go to them, we find functions which are significantly longer. Let's take a look at the disassembly, for instance. It's a graph. So here we find definitely some obfuscated functions. Not all of them are obfuscated, but some of them are obfuscated. So, and now we basically observe that in that folder we have some other shared object files. We also saw that at.so beforehand, but if we take a look at that, it just says it's data. So it's not a valid ELF file here. So we can conclude, or we can assume, that if that is some kind of code, it's probably packed or encrypted. So let's take a look in the strings here if we do something like with SO files. And indeed, we find this string at.so in the same folder with a reference here. And then we can check in the decompiler, and then we see here's a function that takes this at.so as parameter and afterward returns something, and this one goes into another function with the string run_dll. Let's take a look at that function, and basically if we do that, we will see that this function is one of the functions which is obfuscated quite a bit. So while now we could try to take a look at the code, understand it, maybe deobfuscate it or so on, so this would slow us down and take a lot of time, depending on the tools we have in our tool chain and so on. So, but maybe there's a better way. So if you think about, we have this at.so. We know that this is some kind of encrypted or packed code. And then we see that this one is loaded into memory, then some obfuscation, and then a string run_dll. So an educated guess might be that this function here performs some kind of unpacking or decrypting in memory. And so we could just give this to an LLM, give it 5 minutes, and see if it can figure out something interesting. So we can now go to the LLM and tell it, well, let's stop that here and let's tell it you already dumped, and give it the file name, launcher random base name. This one seems to unpack or decrypt in memory the file at.su in the function, that one. Analyze the code and see if you can decrypt the code, unpack it. So, and with that, we can just let it work and analyze further or take a look or so on. But in that case, let us go back to the other agent. And this one is the queuing EDR killer, which basically we told it to annotate the database. It told us it did so. And so we can just ask it, give me concrete locations you annotated, that we can double check. And in the same time, we open that. So this is under samples. Here, this is the database. Looking at the function names, we already see that it annotated quite a lot of function names. So it for sure did something. So yeah, it definitely did something. And let's say if it says anything, it says it renamed the functions. Okay, we already saw that. It also added some comments. So let's take a look. Let's, for instance, take that address. Take a look here. And indeed, it added a comment which hash says. So yeah, here again, it's pretty useful and can take us and can take a lot of work from us. Okay, that said, let's go back to the other agent. And oh, this one already said it doesn't decrypt ATSO. It unpacks it with an APLib, which is a common packing algorithm, compressed wrapper. And it just told us it wrote an unpacker script and it instructed it. So now let's take a look. And indeed, we now have a folder unpacked. And let's do a file command here. And this one looks significantly better. Now we have all the things unpacked. So now let's load the at.so. And take a closer look. It has some functions. It looks like, and this, let's take a look. This looks like code, and this looks like obfuscated code again. So yes, we can say it was definitely successful. And now we could continue with the next stage and analyze that part and so on and so on. So it's important to note here that it was basically able to decrypt, to understand the logic of the unpacking and wrote a custom unpacker for that. But the question is if it did bypass the obfuscation, the obfuscated code or so. So let's just ask the agent, what did you do with the obfuscation? Did you understand the entire code? Or how did you know? And let's see what it says. Okay, and so basically it was able to understand parts of the loader, but made the most of the context not from the obfuscated code, but from the surroundings, like the open part, the read parts, the loading parts, and so on. And so therefore, here the deobfuscation hasn't been really required. It was able to bypass it and get enough information to know which algorithm is behind that. So we can just ask it, how do you know it was a how was it called? That one. And let's see, because my guess would be exactly. It found some characteristic constants and lengths and so on. So it wasn't basically able to fully analyze the entire algorithm. It was more like pattern matching and then giving it a try. And this is an important thing. We could, of course, since we see that the obfuscation is all over the place, we could ask to deobfuscate that. But if we would just ask to deobfuscate that out of the box, it would take a lot of time. Like, let's say I could give it a function like analyze that function and deobfuscate it. Then it would probably do something and it would understand that this is control for flattening and so on and so on. But it wouldn't probably correctly derive everything or get a clean solution or write a clean deobfuscator that all functions are clearly deobfuscated and so on. So there are too many ways to do that and too many things that you can do wrongly and so on. And there's not enough verification on the automation side that can tell the LLM or the agent if the deobfuscation is right or not. So by just telling it deobfuscate everything, you will probably get a result, but it doesn't look good or doesn't look correctly. So the pure deobfuscation would be significantly harder. To do that, you would have to know how this obfuscation here works. You would need to take it more at hand and tell it like, hey, we want to, for instance, write a custom decompiler pass for Binary Ninja that targets control flow flattening, and then tell it how it works and what it shall do. With this kind of guidance, the results are probably pretty good. And then you can get like a decompiler pass for Binja, or if you do it for Ghidra and so on, that provides good results. But if you tell it out of the box, please deobfuscate that, I don't expect that the results are good in any way. Okay, so we had basically 3 different scenarios. We basically used the agents for structured tasks where we gave the agent guidance like, hey, I know that this is roughly that, please analyze that, please do that for me, please annotate that for me. And so we did it on string decoding, API resolving, and unpacking. And these are just some examples, and we could do it on very complex examples. We can do it hand in hand. We basically use it as our agent, as our reverse engineering buddy, that we can just ask stuff, give it stuff, and so on the site. And so guide manual analysis, but we basically orchestrate that. However, we can also do it another way around, that we do entirely automated analysis to get at least some initial triage. So what we could do is we could build something like some autonomous analysis pipelines. So the task automation we did. And if you want to redo that, you have all the samples on your own in the GitHub. You have all the links to have more information about the samples. But now let's talk about pipelines. So the idea is that agents are good in supporting individual analysis, but they can also orchestrate analysis workflows on their own. And so especially they can do a structured multi-phase investigation. And here it is important to enforce some structured documentation. So the idea of that has been written by me in a blog post some weeks ago. You basically find it on my homepage on this article. So here we first give a short introduction into agents and so on and so on. But then we basically have this analysis pipeline. And in this analysis pipeline, we basically have multiple stages. And in the first stage, we basically query a lot of different tools that extract information or some basic information. Like we extract API imports, we extract strings, we do a crypto detection, we perform some Jara checks and so on. So we basically do some kind of fact checking and run a lot of common tools that a typical malware analyst would also run to get a high-level overview. And then we dump all kind of artifacts. And then in the next step, we let the agent review these artifacts. Then tell it, hey, what is interesting, what is not interesting. And based on what you see, build some hypotheses, what might be true, what might be false, what might be interesting to look at. So for instance, if you see something like API imports that indicate keylogging, it might come up with a hypothesis, it might be a potential keylogging. And then, only after this hypothesis have been generated, it can then start an MCP server like the Ghidra MCP or the Binary Ninja MCP and open that and explore on its own and then validate the hypothesis and so on. And the important thing here is that we have to enforce like a persistent state. Like, hey, for everything you do, extract all the information you have and dump them into the file system. After each iteration, dump everything that you analyzed and that you hypothesized and document it. Like we have to enforce detailed documentation. And if we have orchestrated pipeline like that we, for instance, can put into an agentic skill, then we get a lot of different or results that are useful. So like, let's say this initial triage run might then run for 15 or 30 minutes, but afterward we get a pretty good high-level overview about the functionality. So in another repository on my Git called Agentic Malware Analysis, we basically have exactly that setup, where we have a dedicated Docker container with MCP servers and all kinds of tools installed. And then we have a so-called skill. And that skill basically tells the agent how to follow a procedure. And if we take a look at that, we basically see here we say create a directory called status, create these, read these artifacts. Then we provide a checklist. We tell it which scripts to run, how to organize the repository, how to decide what to do next, what tools it has available, and so on, how to use that tools. So then we say it, hey, like create these files. And then, for instance, we can take a look at one of the, so here we have scripts then, and these scripts basically we see some collect imports, other collect strings, then we rank the signals, we scan with kappa and Jara and so on. And somewhere we then have like a checklist, and there we tell it what to take a look at and so on and so on. Maybe we have also some templates, like where we say, hey, in the final report, organize it like that, and a priority queue and so on, that you prioritize on your own, which is the most important thing to analyze first and second and third, and so on and so on. And once we've done that, we can just query the agent with something like, where is the blog post? We can just query the agent with something like analyze the malware sample, give me a detailed overview, and use a skill. We basically tell it to follow the specific skill, and then it does it on its own. Here in this example, it took like 17 minutes. And in that the malware sample we analyzed here is basically a German state Trojan, which has been like a governmental malware, which uses a cryptographic algorithm with a hard-coded AES key and so on. And here in the if we take a look at the results, I only have the results here because it took too long otherwise. We basically have this status folder. And here we see that this is a status folder. And if we take a look at that, we then see basically the artifacts. So if we take a look at the raw strings, we see here it just extracted all the strings. But if we take a look at some other things, like for instance the hypothesis, then it gets something like it has some ideas about the persistence and which functions are on that it can do keyboard device operations, browser and Skype related collections and so on. So it creates some hypothesis, and then it later on creates a deep analysis plan where it basically tells us, hey, this one is something I want to do. I want to trace that one. I want to do that one, and so on and so on. And finally, we also have like this analysis draft where it then tells us, hey, I know this is a sample. Its entry is there. It does surveillance of Skype, Explorer, MSN Messenger, and so on. It uses persistence in these functions and tells us basically high level what to do. We can also take a look at screenshot capture. It basically tells us where the interesting things are. It tells us the CNC server, like the port and the IP address of the CNC server. If we take a look, it also analyzed the entire protocol, like the banner it sends, the port, and so on. If we take a look at AES, for instance, it also tells us that it uses AES with a fixed key. So as we can see, if we just let it run on its own for a few minutes and then maybe tell us, hey, just continue with deep analysis or something like that, it does a lot of stuff on its own, and we can come back later on and take a look at that. Does that mean that everything here is correct? No, of course not. it's LLMs, it's agents. They know how to use tools and they can do some kind of reasoning and so on. However, they can still hallucinate, they can get stuck, they produce false positives and so on and so on. So the important thing is that we don't believe them, that we just take them as input to validate on its own. And however, given that, not every detail here is correct, but we get a pretty good overview and understanding and can then cross-check on our own if that works, if that is correct, and so on. So this is an enormous speed up. That doesn't mean they replace reverse engineers or something like that, or that we don't need to learn reverse engineering anymore. It mostly means they can automate annoying stuff, and we have to have the knowledge to check and validate if it's correct or not. But they can make us significantly more productive. So if you want to play around with that, you can take a look at the blog post or you can take a look at the entire repo here. So to wrap up, and afterward I will come back to the questions. So to wrap up, the results of the agents are non-deterministic. And then they might run out of context window and so on and so on. And complex tasks need analysis guidance and observation. And especially we need to verify the result. So these are essential things. However, if we take an agents and give them focused tasks, they can do a lot of cool stuff for us. And we can also automate parts of that by doing by chaining tools, by chaining skills and so on, and then having some automated analysis pipelines that at least scale away some of the work. So, however, the important thing stays that the analyst has expertise, takes a look what to do, and knows how to work with that. And that we drive basically the analysis. So basically, if you want to check it out on your own, the recording will be available later today or at latest tomorrow. So you have everything important here in this repository. And also, if you like the stuff and want to learn more about, like, for instance, basic reverse engineering, how to do reverse engineering, how to do malwares, and so on, I give trainings on that. Or if you are more advanced and want to do something like, hey, how to deal with obfuscated code, how to use agents for deobfuscation, or how to understand how to write deobfuscation tooling on your own, and so on. If you have that need, feel free to come to my trainings, software deobfuscation techniques that I'll give at Recon and Hexacon this year, but also I'm open for private trainings. So if this is something for you, go to my website, check it out, and maybe we see us somewhere. So that's from my side. Let's take a look if there are any questions. There's a question if I'm free for some projects. Yes, I am. So if you have something interesting, just drop me something. There's another question. What's the number one issue you are seeing with agentic pipelines and how are you mitigating those problems? I would say the main issue, it depends on the use case and on the pipeline and your analysis goal. But like, sometimes they get stuck and so on. But I think the two main problems are getting out of context, like losing context and losing information. This is one thing. And the other thing is producing results, but having no possibility to validate them. Or the agent has no possibility to validate the thing because it lacks expertise, it lacks tooling, it lacks access. So to deal with the part of getting out of context, there it's important to drop as many information as possible to the file system. Basically, use the file system as some kind of extended memory. Like we've seen it here, that we tell the agent dump everything, also like we see in the folder disassembly or decompilation, it basically dumped functions to the file system and so on, such that it doesn't have to query the tools all over and so on. So basically dump all kind of information you have to the file system and let the agent reiterate it, reread it, write down its sorts and re-evaluate it over time. Reverse engineering itself is a pretty iterative process, and so are agents. So basically, by letting them dump information, taking a look at them, re-evaluating and updating the information, this is basically the same workflow we humans would work. And so dumping a lot of stuff to the file system is the way to go. It doesn't solve everything, but it makes it at least way more reliable. The second problem, as said, is validation. And the question is always, how can I validate results? And there's no generic answer for that, because that is always like a problem specific. In the Mirai case, the verification was quite simple. So like here, we knew the algorithm, we knew that one, and we could try it on our own, and it was fine. With the API resolving, well, this is something where we have multiple ways. We can just first assume that it works. We can take a look and inspect the code it wrote and then analyze within decompiler output and say, hey, might work, might not work, and come up with that. Or we might execute it dynamically and check with breakpoints that these things are correct. So maybe we don't need to verify everything, but just a few points of interest here and there to validate at least partially. So in the extraction phase, that was quite easy, because then we could just do a file command if it looks, and either it worked or not. So when it was encrypted, it was just data, and when it was correctly decrypted or decoded, it was like a valid ELF file. So that was also a good validation. But as said, these things are highly problem specific. And especially coming to obfuscation again, their validation is significantly harder, and there you have to have a very good understanding of these things. And therefore, it's pretty unlikely that the agent can validate on its own in a good or reasonable way, so we have to interfere there. So basically, in short, verification is highly problem or domain specific, and for the getting lost and getting out of context part, intermediate solution is at least dumping a lot of information on the file system. Let me check if there are any other questions. It doesn't look like that. So, okay. Then, with that said, thanks a lot for your interest. I hope you learned something interesting. And if you have any questions or something like that, just feel free to reach out. You have my contact details on the slide deck and on the Git. If you want to play around with that, just do that. So, and otherwise, thanks a lot for your attention and have a good day. Goodbye.